Space and Science News. With James. The year is 2025. Humanity's quest to unravel the universe's deepest secrets just got a massive upgrade. Forget your standard visible light telescopes, we're talking about an entirely new way of seeing the cosmos. In March 2025, NASA successfully launched the spectrophotometer for the history of the universe, epoch of reionization, and ICE's Explorer, or SPHEREx for short. This isn't just another space telescope, it's a mission poised to deliver an unprecedented, all-sky map in a part of the light spectrum we rarely hear about, the near-infrared. Now, why near-infrared? Think about it this way, visible light, the kind our eyes see, gets easily blocked by dust and gas clouds in space. It's like trying to see through thick fog. But near-infrared light can cut right through that cosmic haze, revealing what lies beyond. This capability is absolutely crucial for SPHEREx's ambitious goals. Imagine being able to peer back in time, not just to the formation of galaxies as we know them, but to the very first moments after the Big Bang itself. That's one of SPHEREx's primary objectives, to understand cosmic inflation. Cosmic inflation is this mind-bending theory that proposes the universe expanded exponentially in a tiny fraction of a second right after the Big Bang. It's what smoothed out the universe and set the stage for everything we see today. SPHEREx isn't directly seeing inflation, of course, nothing can. Instead, it's looking for the subtle fingerprints left behind by this rapid expansion. By meticulously mapping out the distribution of hundreds of millions of galaxies across vast stretches of space, SPHEREx aims to create a 3D cosmic atlas. This map isn't just pretty pictures, it's a treasure trove of data. The way galaxies cluster and distribute themselves on the largest scales can reveal hints about the early universe's expansion history. If inflation happened, it would have imprinted a specific large-scale structure on the universe, and SPHEREx's wide-field, all-sky survey is uniquely positioned to spot that. Beyond the vastness of cosmic inflation, SPHEREx also has its sights set on something far more fundamental to our existence: water. Yes, water, the very molecule that makes up oceans, clouds, and every living thing on Earth. One of the enduring mysteries in astrophysics is the origin of water in our galaxy, the Milky Way, and indeed, across the universe. Where did it all come from? How did it end up on planets like ours? SPHEREx is designed to trace the cosmic journey of water in a wide array of organic molecules, the building blocks of life, from their origins in interstellar clouds to their presence in newborn planetary systems. It does this by using its spectrophotometer. This isn't like a camera taking a single snapshot. A spectrophotometer breaks down the light from every point in the sky into its constituent wavelengths, creating a kind of cosmic rainbow for each celestial object. Every element and molecule has a unique spectral signature, like a barcode. Water, for instance, has distinct absorption and emission lines in the near-infrared. By detecting these specific spectral fingerprints, SPHEREx can identify where water exists, in what form, ice, vapor, and in what quantities, whether it's in dusty protoplanetary disks around young stars, within comets, or even in the atmospheres of exoplanets. The scale of this undertaking is staggering. SPHEREx will survey over 450 million galaxies, collecting data on billions of stars, nebulae, and other celestial objects. It's not just a targeted observation of a few interesting spots, it's a comprehensive scan of the entire sky, repeatedly, over its mission lifetime. This repeated scanning is crucial because it allows scientists to build up incredibly detailed and accurate spectral maps, filtering out noise and enhancing faint signals. Even in its earliest phases, the mission has lived up to its promise. NASA engineers and scientists were absolutely thrilled when the first instrument checks came back clean. The data flow began almost immediately, and the initial releases, while preliminary, have already started to turn heads in the scientific community. Think about it. Within weeks of launch, new, raw data streams were hitting servers worldwide, sparking a feverish analysis by astronomers and researchers. What makes these early data releases so exciting? It's the sheer volume and uniformity of the data. For the first time, researchers are getting an all-sky near-infrared survey with this level of spectral detail. Scientists who had been working on models for cosmic inflation are now eagerly comparing their predictions to SPHEREx's early galaxy distribution maps. And those studying the cosmic water cycle are poring over the spectral barcodes from distant stellar nurseries, looking for clues to how water forms and travels across the galaxy. One particular area of intense focus has been the data related to molecular clouds, the vast interstellar regions where stars and planets are born. These clouds are rich in dust and gas, making them opaque to visible light but transparent to SPHEREx's near-infrared gaze. Scientists are using SPHEREx to peer directly into these stellar nurseries, identifying signatures of water ice on dust grains, and water vapor in the warmer regions. This is giving them an unprecedented view into the very first steps of planetary formation, understanding how water, a fundamental ingredient for life, gets incorporated into nascent solar systems. The discussions among astronomers are lively. Early findings are being shared at virtual conferences and through preprint servers, with initial interpretations sparking both excitement and debate. For example, some early data concerning the distribution of galaxies on super-large scales has already provided valuable new inputs to cosmic inflation models, allowing scientists to refine their calculations and narrow down potential scenarios for the universe's rapid expansion. On the water front, there are early indications of unexpectedly high concentrations of complex organic molecules alongside water ice in some distant star-forming regions, suggesting that the chemical ingredients for life might be even more prevalent than previously thought. The analysis is ongoing, of course. These are just the initial glimpses, the first few puzzle pieces of a colossal cosmic picture. But what SPHEREx is showing us already is a universe even more dynamic and complex than we imagined. The sheer amount of data, the consistent quality, and the unique spectral perspective mean that every new data dump is a potential game changer. It's not just about confirming existing theories, it's about opening up entirely new avenues of inquiry. The scientific community is holding its breath, waiting for each new batch of information, knowing that some truly revolutionary discoveries are on the horizon. The excitement around SPHEREx wasn't just confined to big scientific conferences, it permeated the online astronomy communities, news outlets, and even general science enthusiasts. Every week seemed to bring a new tidbit from the early data releases. But while the cosmic inflation findings were fascinating to cosmologists, it was SPHEREx's insights into water that really captivated the broader public. After all, water is relatable. It's life. And SPHEREx was painting a picture of a universe far richer in water than many had previously imagined. One of the most compelling early findings came from SPHEREx's detailed mapping of protoplanetary disks. These are the swirling, dusty nurseries around young stars where planets are born. Before SPHEREx, our view into these regions was often obscured by the very dust and gas that formed them. But with its near-infrared capabilities, SPHEREx could peer deep inside, essentially seeing the chemical blueprints of emerging solar systems. The results were quite stunning. Spectral signatures of water ice were far more prevalent and widespread within these disks than earlier, less comprehensive surveys had indicated. This wasn't just about detecting water, it was about understanding its distribution and abundance. SPHEREx was able to map out regions within these disks where water ice was particularly concentrated. For instance, in several dozen observed protoplanetary disks, SPHEREx identified a clear, snow line, the boundary beyond which water transitions from vapor to ice. But what was surprising was the amount of ice detected within and beyond this line, suggesting that early solar systems might inherit a substantially larger reservoir of water-rich material than current models assumed. This had immediate implications for how easily planets could acquire their oceans. If the building blocks are more abundant from the start, then the path to a water world becomes much more straightforward. Beyond these young stellar systems, SPHEREx also began to unveil new details about water's presence in interstellar space. We've known for a long time that molecular clouds, the giant nurseries of stars, contain water. But SPHEREx provided an unprecedented, fine-grained map of water vapor and ice within these vast structures across our galaxy. Scientists had always theorized about the journey of water from these clouds into comets and then potentially onto planets through impacts. SPHEREx's detailed spectral maps provided direct observational evidence supporting this journey, tracing the chemical lineage of water from diffuse gas to denser regions where it freezes onto dust grains, waiting to be incorporated into new planetary bodies. For instance, in the Orion Molecular Cloud Complex, a well-studied star-forming region, SPHEREx detected intricate filaments of water vapor flowing towards protostars, and vast reservoirs of water ice locked within the colder, denser pockets. This wasn't just a blob of water, it was a dynamic, evolving system, where water was actively participating in the cosmic cycle of star and planet formation. The data showed distinct variations in water composition and temperature across these regions, allowing scientists to piece together the specific chemical pathways involved. What emerged from these early findings was a broader picture. Water isn't just an anomaly on Earth, it's a cosmic constant, an ingredient that appears to be far more ubiquitous and actively involved in the formation of stars and planets than many had previously thought. This revelation has profound implications for the search for life beyond Earth. If water, a fundamental requirement for life as we know it, is so prevalent, then the number of potentially habitable exoplanets could be significantly higher. The data was so rich, in fact, that it sparked a lively debate within the exoplanet community. Are we looking at a universe teeming with water worlds, planets where liquid water is not just present but dominant? SPHEREx's all-sky survey provided the raw statistics needed to make such estimations on a truly galactic scale, moving beyond mere speculation based on a few observed systems. The sheer volume of water detected in various cosmic environments hinted that the conditions for forming water-rich planets might be the norm, rather than the exception, throughout the Milky Way. Of course, detecting water from billions of light-years away is one thing, understanding its exact forms and temperatures is another. SPHEREx's near-infrared capabilities are excellent for this. Different forms of water, vapor, liquid, ice, absorb and emit light at slightly different wavelengths in the infrared spectrum. By precisely measuring these spectral shifts, SPHEREx allows scientists to distinguish between these states and even infer temperatures. This level of detail is crucial for determining if water exists in conditions suitable for life, not just as frozen ice, but as liquid. The data continues to flow, and with each new release, the picture becomes clearer. SPHEREx is doing more than just mapping, it's revealing the chemical tapestry of our universe, showing us that water, and the ingredients for life, are woven into its very fabric. It's a fundamental understanding that shifts our perspective from Earth as a unique water oasis, to potentially one of many in a vast, water-rich cosmos. This deep dive into the cosmic water story is just beginning, and the implications for astrobiology and our understanding of habitability are just starting to unfold. While the insights into cosmic water were captivating, SPHEREx's other primary mission goal, exploring cosmic inflation, was delivering equally groundbreaking, if more abstract, data. Cosmic inflation is arguably one of the most profound and mind-bending theories in modern cosmology. It suggests that in the tiniest fraction of a second after the Big Bang, the universe underwent an unimaginably rapid, exponential expansion. This burst of growth stretched the infant universe to immense proportions, smoothing out any initial irregularities and setting the stage for the large-scale structure we observe today: galaxies, clusters of galaxies, and vast cosmic voids. Think of inflation as a cosmic growth spurt. Without it, our universe would look very different, likely much lumpier and less uniform than it is. The evidence for inflation primarily comes from observations of the cosmic microwave background, CMB, the faint afterglow of the Big Bang. Tiny temperature fluctuations in the CMB are believed to be the seeds from which all structures in the universe grew, and their pattern strongly supports the idea of inflation. However, the CMB only gives us a snapshot of the universe when it was about 380,000 years old. SPHEREx aims to provide complementary data by mapping the universe's structure on even larger scales, looking at the distribution of galaxies across billions of light-years. SPHEREx does this by essentially creating a three-dimensional map of the cosmos. By measuring the distance to hundreds of millions of galaxies, it can plot their positions in space. When you look at this map, you don't see galaxies randomly scattered. Instead, they form a vast, intricate cosmic web, filaments of galaxies stretching across enormous distances, punctuated by gigantic voids where very few galaxies reside. It's like a colossal sponge, with the galaxies clustered along the sponge's material and the voids as the empty spaces. The pattern of this cosmic web is a direct echo of the conditions in the very early universe, long before galaxies even formed. One of the key measurements for studying inflation using galaxy surveys is something called baryon acoustic oscillations, BAO. This is a mouthful, but it's a relatively straightforward concept. Imagine ripples spreading out in a pond after a stone is thrown in. In the early universe, before matter and light separated, sound waves traveled through the dense cosmic plasma, creating pressure waves. When the universe cooled enough for light to escape, forming the CMB, these sound waves left a characteristic imprint, a preferred separation scale between galaxies. This preferred scale acts like a standard ruler in the universe. By measuring how big this ruler appears at different distances, cosmologists can determine how the universe has expanded over time. SPHEREx's unprecedented all-sky coverage and detailed spectral information make it exceptionally powerful for measuring BAOs. Previous galaxy surveys were limited by their field of view or the precision of their distance measurements. SPHEREx, however, is mapping over 450 million galaxies across a massive volume of space, providing the statistical power needed to detect these subtle BAO patterns with incredible precision. Even in its early data releases, the quality of the galaxy distribution maps has exceeded expectations. During the initial data analysis phases, teams of cosmologists began feeding the raw SPHEREx galaxy catalogs into their complex simulation models. What they found was both confirming and incredibly exciting. The first BAO measurements from SPHEREx data aligned perfectly with existing models of cosmic inflation derived from CMB observations, strengthening the overall case for this theory. This was a significant validation. It showed that two completely different observational techniques, looking at the universe when it was 380,000 years old and looking at the universe when it was billions of years old, yielded consistent results regarding its early expansion. But the excitement didn't stop there. As more data came in, and as the 3D maps became denser, SPHEREx began to reveal something even more subtle. Beyond the standard BAO signal, some cosmologists started to identify faint anisotropies, slight directional preferences, in the large-scale distribution of galaxies that weren't fully predicted by the simplest inflation models. These were incredibly small deviations, easily dismissed as statistical noise by less precise instruments. But with SPHEREx's massive dataset and its uniform, all-sky coverage, these faint patterns started to gain statistical significance. This was a major talking point at internal NASA and university meetings. Could these subtle anisotropies be hints of a more complex inflation model? Perhaps inflation wasn't as perfectly uniform as previously thought, or maybe there were multiple phases to it. Some theories of inflation, for instance, predict the existence of primordial gravitational waves that could leave such a subtle directional imprint on the cosmic structure. While SPHEREx isn't designed to directly detect gravitational waves, the precise mapping of galaxy distribution might indirectly hint at their influence. The early findings spurred new theoretical work, as cosmologists raced to develop models that could account for these newly detected subtle variations. It's like looking at a perfectly smooth piece of glass and then, with a new, powerful microscope, suddenly seeing tiny, almost imperceptible scratches that tell a deeper story about how the glass was formed. SPHEREx was providing that microscope for the universe's infancy. The implications were profound. If these anisotropies held up to further scrutiny, it wouldn't disprove inflation, but it would refine our understanding of it significantly, pushing us towards more sophisticated and perhaps even stranger descriptions of the universe's earliest moments. The universe was starting to whisper secrets about its birth, and SPHEREx was listening. As SPHEREx continued its relentless survey, mapping galaxy after galaxy, the vast cosmic web began to unfold in unprecedented detail. This web, remember, is the universe's large-scale structure, giant filaments of galaxies, separated by immense, relatively empty regions called cosmic voids. These voids are not truly empty, they still contain some dark matter and a scattering of galaxies, but they are far less dense than the filaments. The distribution and size of these voids are crucial for understanding cosmology because they also carry the imprints of the early universe and how gravity shaped matter over billions of years. Previous telescopes and surveys had certainly mapped these structures, but SPHEREx's all-sky, near-infrared perspective offered something entirely new. It could see through dust that obscured distant parts of the cosmic web, giving us a more complete and uniform picture than ever before. This was like finally getting a high-definition, three-dimensional scan of something we'd only seen in blurry two-dimensional images. One of the most anticipated analyses from this comprehensive mapping involved measuring the size and distribution of these cosmic voids. Cosmologists expected to find a range of void sizes, consistent with current models of large-scale structure formation, which are themselves rooted in the principles of cosmic inflation. The theory predicts how matter should clump together and how empty spaces should form under the influence of gravity over cosmic time. However, as the SPHEREx data accumulated and sophisticated algorithms began to reconstruct the 3D map of the universe, something unexpected started to emerge. In addition to the expected range of void sizes, the SPHEREx data began to consistently identify a small number of exceptionally large, seemingly emptier voids than predicted by standard cosmological models. These weren't just slightly bigger. Some appeared to be significantly larger, and with a lower galaxy density within them, than could be easily explained by the gravitational collapse and expansion processes we currently understand. These ultra-large voids seem to challenge the statistical uniformity that our models expected on the largest scales. It's like rolling dice a million times and mostly getting even distributions, but then finding a handful of sequences that seem statistically improbable. Were these just rare statistical flukes that SPHEREx, with its immense data volume, was bound to uncover? Or were they pointing to something deeper, something fundamental about the universe's structure that we hadn't quite grasped? The initial response in the scientific community was cautious excitement. Researchers ran multiple checks, reanalyzed the data for potential biases, and verified the photometric redshifts, how SPHEREx estimates distances to galaxies. Each time, these anomalously large voids persisted. They were real, confirmed structures in the cosmic web. This sparked intense discussions among cosmologists. Could these massive voids be evidence for alternative theories of gravity that operate differently on vast scales? Or perhaps they hinted at the presence of exotic dark energy, the mysterious force driving the accelerating expansion of the universe, that might not be entirely uniform throughout space. Some even speculated about the possibility of cosmic texture or other topological features from the very early universe, phenomena that could leave such large-scale imprints. One particularly intriguing possibility being explored was how these voids might relate to the subtle anisotropies observed in the cosmic inflation data, which we discussed in the previous section. Could the same underlying physics that caused those faint directional preferences also be responsible for creating these exceptionally large voids? If there was some tilt or directionality to the universe's expansion in its earliest moments, it might have led to slightly different rates of structure formation in different areas, resulting in these unusually immense empty spaces. The implications are significant. If these extremely large voids are indeed more common or larger than standard models predict, it means our current cosmological model, the Lambda-CDM model, which combines cold dark matter and dark energy, might need some refinement, or perhaps even a fundamental re-evaluation of certain parameters. It wouldn't necessarily mean the model is entirely wrong, but it would suggest there are aspects of the universe's evolution and fundamental physics that we don't yet fully comprehend. SPHEREx isn't just mapping the known, it's pushing the boundaries of what we understand about the universe's largest, most empty spaces. The story of SPHEREx is far from over. While the initial data releases have already delivered incredible insights into cosmic inflation and the origins of water, the mission is designed to operate for at least 2 years, continuously collecting and refining its all-sky maps. This means we're only just beginning to scratch the surface of the scientific treasures it holds. The true power of SPHEREx lies not just in these early findings, but in the cumulative data it will acquire over its full mission lifetime. As SPHEREx continues its work, mapping the full 450 million galaxies and beyond, the statistical power of its dataset will grow exponentially. This will allow scientists to reduce uncertainties in their measurements, confirm the subtle anomalies we've already discussed, and potentially uncover entirely new phenomena. For instance, the detection of those unexpectedly large cosmic voids and the faint anisotropies in galactic distribution will require even more data to conclusively confirm their statistical significance and explore their true implications. As the map becomes denser and more complete, these hints could solidify into groundbreaking discoveries. One of the most exciting aspects of SPHEREx's ongoing mission is its ability to help in the search for life beyond Earth. By mapping water and a wide range of organic molecules throughout the galaxy, SPHEREx is essentially creating a cosmic inventory of life's building blocks. This data is invaluable for guiding future missions, particularly those searching for habitable exoplanets and signs of biosignatures. If SPHEREx consistently finds high concentrations of water and complex organics in specific types of protoplanetary disks or around certain stars, it helps narrow down the most promising targets for more detailed follow-up observations by telescopes like the James Webb Space Telescope or future observatories. It helps us answer the question, where should we look next for alien life? Furthermore, SPHEREx's comprehensive spectral survey is creating a rich public archive that will benefit astronomers for decades to come. This isn't just raw numbers, it's a detailed chemical fingerprint for hundreds of millions of celestial objects. Researchers worldwide, from seasoned cosmologists to curious students, will be able to access this data and use it for their own studies, making unexpected discoveries that might not even be part of SPHEREx's primary mission goals. It's like building a massive, detailed library of the universe, open for anyone to explore. New theories will be tested, old questions revisited, and entirely new questions will emerge, all thanks to this incredible dataset. The mission is also contributing significantly to our understanding of the evolution of galaxies. By seeing through dust and observing galaxies at different stages of their evolution, SPHEREx is helping scientists piece together how galaxies form, grow, and interact over billions of years. Its unique perspective allows for detailed studies of galactic mergers, star formation rates in dusty environments, and the distribution of cold gas and dust, all of which are crucial for understanding how the universe evolved from its simple beginnings to the complex structure we see today. In essence, SPHEREx is doing more than just collecting data, it's providing the foundational knowledge for the next generation of astrophysical research. It's pushing the boundaries of our understanding of the universe's earliest moments, tracing the cosmic origins of water, mapping the grand structure of the cosmos, and laying the groundwork for the search for life. It's a mission that reminds us of humanity's insatiable curiosity and our relentless drive to explore the unknown. So, as SPHEREx continues to scan the skies, delivering gigabytes of new information every day, the scientific community, and indeed the world, waits with anticipation. The universe is revealing its secrets, piece by astonishing piece, and SPHEREx is one of our most powerful tools for listening to its ancient whispers. Thank you for joining us on this journey through the groundbreaking discoveries of NASA's SPHEREx mission. It's truly a thrilling time for space exploration and our understanding of the cosmos. We hope you enjoyed learning about how this incredible telescope is helping us unravel the universe's greatest mysteries, from cosmic inflation to the origins of water. If you found this information as fascinating as we do, make sure to like this video, subscribe to our channel for more exciting science content, and share your thoughts in the comments below. We hope to see you on the next video. Thanks for watching. Remember to like, subscribe, comment, share and click that notification bell so you never miss out. See you next week.